This lecture is for section 7.3 of Math 311, a course in linear algebra at Western Illinois University. All right, so we are continuing to talk about applications of all the linear algebra topics that we described in the first few weeks. Now we're going to be jumping. We jumped all the way. Right now it seems like we're skipping through a lot of sections to 7.3. And trust me, we don't necessarily need a lot of the material. In fact, everything that we are going to talk about here, we've actually done before, or can be built on what we've done before. Okay, so this is still more or less self-contained. We're talking about some really neat applications in the world of statistics, and it's called least squares approximation. And I'm going to start off with a somewhat dumb example. Here we have a system of equations, 3 equations, 2 unknowns, and it's pretty clear that this is inconsistent. This is nonsense, right? X plus y cannot equal 1 and 3 at the same time, right? So why would we even consider this? Well, first of all, we can still write this as a matrix equation, right? We can still write this as 1, 1, 1, 2, 1, 1, times the variable vector xy is equal to 1, 5, 3. All right. If we call this matrix A, we can call this vector x bar, and we can call this B. Okay. So we don't have, if we consider this equation ax equals b, this does not have an exact solution. Okay, obviously. So why would we even consider it? Well, let's see what would be the next way to do this. If it doesn't have an exact solution, that is, if ax minus b can never be 0, well, what's the smallest ax minus b could be? All right. The question is, well, what's the smallest value of, well, not ax minus b, because that's going to be a vector quantity. Well, we can talk about, we can't say one vector is bigger than another, but we can talk about the length of a vector being bigger than another. Okay, so what we could say is, what's the smallest value of the length of ax minus b? All right. Now again, okay, why would we want to do that? Well, let's look at this from a slightly different perspective. Okay, let's replace the x and y with an a and b, and in particular, let's say we had b plus a times 1 equals 1, b plus a times 2 equals 5, and b plus a times 1 equals 3. This is basically the same equations here, except we've replaced the variables, and we've inserted a 1 here in a couple of cases. Well, what this is, if we look at the, we'll see that this corresponds to some points, the point 1, 1, 2, 5, and 1, 3. Okay, this basically, if this equation were to hold, that would mean that these points are all on the line given by y equals ax plus b. Now, of course, this is impossible, because this is impossible, and we can see it geometrically, right? If we plot these points, here's 1, 1, 2, 5, and 1, 3. There is no way that we could get a line passing through all 3 points, especially since these two have the same x-coordinate. But the question is there a line that might kind of approximate these points? Is there a line where the gaps or the errors are as small as possible? Okay, and this is actually those of you who had statistics, we're talking about regression. If we plot data points, how can we find the best fit, the best line that would approximate these points, right? And that's why we're kind of interested in this. In this case, though, we'd be looking for A and B, where A is, of course, the slope. This would be the line y equals ax plus b. This would be A would be the slope and B would be the y-intercept. But this is really what more importantly, these would be the variables of this equation that we're trying not to solve anymore, but to minimize this. So the question is, okay, how can we minimize something like this? Well, if we look at this again, remember that AX is going to be a vector, and it's going to be in the column space of A. So another way we want to find this, we want to find X such that AX is the vector in the column space of A that is closest to B. So that's what we want to, that's what we're going to be doing here. That's another way of looking like this. And remember, the column space of A, that is a subspace, and in fact we can make this even more general. That is, if W is a subspace, and V is a vector in Rn, question is, what's the closest? Find the closest. Find the W, the little w and big W that is closest to V. And by closest we mean the difference, their distance is the closest, that is the smallest. The length of the difference between W and V is the smallest it can be. Now, such a vector like this does exist, and it's actually going to be the projection vector, for projection of V into W. So that's what we're going to prove right now. And then we'll come back to this problem at the end. Okay, now, in your notes, I've put down about 4 different little things, or facts, that they're not terribly hard to, well, the proof, I've already given you proofs of these. And the, these are things you should keep in mind, but we're going to be using these very soon. So first to go again for this discussion on page 2, W is a subspace of Rn, V is a vector in Rn, and little p is the projection of W onto V. This is the projection we used with the that we found out how to compute using an orthogonal basis. Okay, so focus on that a little bit. Okay, hopefully that helps. So the first thing we're going to show is that the V minus P is orthogonal to every vector in the subspace W. Okay, and this is where we use the fact that we have an orthogonal basis. Okay, we know that every basis has an orthogonal basis. Let's call it U1 through UK. And so P, of course, we had the formula for the projection. P is going to be this linear combination lambda 1 U1 up to lambda k UK, where lambda I is the dot product of V and UI divided by the dot product of UI with itself. And then V, if we take V minus P, this looks like this. And if we take the dot product of this with UI, you notice because the UIs are orthogonal, all these terms cancel out except the ith term here. And UI times dot V minus lambda I times UI dot UI. We saw this before, things cancel out and we get 0. So this is in fact, so this V minus P is orthogonal to u sub I. and in fact it's orthogonal to every UI in this basis, and therefore it has to be orthogonal to everything in W. Okay, I'll let you look through this, but things trust me, things cancel out. Okay. The next thing that sort of answers what we were talking about before is that if the distance between V and P is less than or equal to the distance between V and W for any vector W in big W, and we only get equality if W is in fact the projection vector P. Okay, so we say that this kind of answers the fact that P in fact is the vector in big W that is closest to V. Now, why is this true? Well, we take the what we're going to do is we're going to first take the square of the distance between V and W, and we're going to do a little algebra trick. We're going to add and subtract P here, and the thing here is if we consider this difference and this difference, these are orthogonal to each other. We know that P is in big W and little w is in big W, so their difference is in big W because big W is a subspace. And we know that V minus P is orthogonal to everything in big W, so it's orthogonal to P minus little w. And because they're orthogonal, we can use the Pythagorean theorem that says that this distance is equal to this thing squared plus this thing squared. Okay, so this is the Pythagorean theorem. Okay, if you go back to chapter 1 or 2, we talked about that. And because notice that these are both P minus W, the length of P minus W squared, it has to be a non-negative number. So this is always going to be greater than or equal to this V minus P squared. Okay, and the only way that you'll get equality is if this is 0, and the only way this is 0 is if P is equal to Q. Or W is equal to P. Sorry. Okay, so that shows that P. This is the smallest you can be. So P is little p. The projection is closest to the closest element in big W to little v. All right. And now we have to, before we go on any further, this might seem a little strange, but we're going to go back to some linear algebra and talk about null spaces here. We're going to find, and in fact, let's see, do I want to talk about this? Let's see, yes, okay, well maybe I'll come back to this in a moment. So we go to page 4. Now, we're going to broaden our thing a little bit. We're going to let A be an m by n matrix and B be a column vector in Rm. And so, based on what we just had, we have to minimize the, if we want to minimize this quantity, we need AX to be the projection of B onto the column space of A. Okay, by number 2, which is what we just proved, right? Where in this case our subspace, capital W, is the column space of A. All right. Now, we could go ahead and before we start using the projection formula, this could be a little messy, but fortunately we have something else to work with. We also know that AX minus B is orthogonal. If this is indeed the projection, then AX minus B is going to be orthogonal to all the vectors in the column space of A. Right, because that's, once again, that's our subspace W. If that's the case, then we're saying that AX minus B has to be in the orthogonal complement of the column space of A. And remember, we did have an exercise where we showed that the complement of the column space of A is actually the null space of A transpose. Okay, so if AX is what it's supposed to be, then this is in the null space of A transpose, which means that A transpose times this difference has to be 0. And we can distribute the A transpose and put this over here. and we get that A transpose A times X equals A transpose of B. And this is what we call the normal equation system for this. And then to find X, we're basically all set as long as, we can, if A transpose A is invertible, we're guaranteed a solution. Okay, but in either case, if X bar, and I messed this up, it should be X equals X bar is a solution to this, we say that X bar is least squares solution to AX equals B. So we're not saying that AX equals B, but what we're saying is that this is going to, the least squares solution means that the difference between AX, the distance between AX and B is as small as possible. Okay. We get a very nice result that says that if A has independent columns, then A transpose A is invertible from number 3 and number 4, which we're about to prove, and that X is unique, and that we can in fact, X then is just going to be the inverse of A transpose of A times A transpose times B. And trust me, everything, all the dimensions here should work out. Okay, so now we want to do, well, why are we guaranteed that A transpose A is going to be invertible if we have linearly independent columns? Okay, so that's what number 3 is about. And so what we have here, first we're going to show that if A is an m by n matrix, then the null space of A is equal to the null space of A transpose A. Notice that we don't need A to be a square matrix anymore, right? Okay, so let's see, why is this true? To show this, we need to show that everything in here is in the null space of A transpose A. Well, that's true because if V is in the null space of A, then AV equals 0, and then A transpose AV, we can just rewrite this as A transpose AV, and AV is 0, so this is 0. So V is going to be in the null space of A transpose times A. Conversely, if V is in the null space of A transpose times A, then A transpose AV is 0, and we take the dot product of AV with itself, we can see that we get V transpose A transpose V, and then this, we know that that's 0, so we get V transpose dot 0. The 0 vector is just 0, the scalar. So we can see the length of AV is 0, so that means AV has to be 0. So V is in the null space of A. Okay, so these two subspaces are the same. Okay. All right. So let's look at what is that. How does that help us in number 4? Well, number 4 says that if A is an m by n matrix, then the rank of A transpose times A is equal to the rank of A. And why is this true? Well, we have. Hold on 1 minute. Okay, I turned the light on, so hopefully this will be a little easier to read. If A, first of all, we can check that A transpose A is a square matrix. In fact, it's m by n because this A transpose is n by m. This is m by n, so this is going to be n by n. And by the rank, so the number of columns in here is n. And by the rank, we can apply the rank theorem to both A transpose A and also A. You get the rank of A transpose A plus the nullity of A transpose A equals n. But that's also equal to the rank of A plus the nullity of A. And we just showed that because of number 3, as a result of number 3, we get the nullity of A transpose A is equal to the nullity of A. So we can see that these essentially cancel out. Remember, the nullity is the dimension of the null space. So if the null spaces are the same, the nullities are the same. And then that means that the rank of A transpose A is equal to the rank of A. Okay? Okay. And remember, the rank is the dimension of the column space, in a row space of a matrix. So in particular, this will, if A has n linearly independent columns, that means the rank of A is equal to n, which means this is equal to n, which means that this is invertible by the fundamental theorem of invertible matrices. Okay, so that's why. All right, so I mean, just to say that, so if A has n linearly independent columns, that means the rank of A is equal to n, and that means the rank of A transpose A is equal to n, which means that A transpose A is invertible. Okay. So that proves that part on the page we were looking at. That's why if A has linearly independent columns, A transpose A is invertible, and in fact we can find the least square solution where we have the inverse of A transpose A times A transpose times B. And this is not okay. It looks like it's nasty, but the important thing is it's the formula, and it's doable. It's calculatable. It's not as hard as you would think. So let's go back to our example here. I left a blank spot page on number 5. So remember, if we remember what we were looking at, we had A was the matrix 1, 1, 1, 2, 1, 1, and B was the column vector 1, 3, 5, and X was the vector XY. We wanted to find the least square solution to AX equals B. Okay, so first of all, A transpose A is going to be 1, 1, 1, 1, 2, 1, that's 1, 1, 1, 2, 1, 1. And when you compute this, this is 3, 4, 4, 6. It's a 2 by 2 matrix. By the way, I should say maybe before we got started, we can clearly see the columns of A are linearly independent because they're just two of them and they're not multiples of each other. So we know that. This is invertible. You can use the formula for the determinant for 2 by 2 matrices. The determinant here, that would be 18 minus 16, so that's 2. So the inverse is 1/2 times, I believe the formula says this is 6, 3, minus 4, minus 4, and this is 3, negative 2, negative 2, 3/2. Okay. So that is the inverse. If you multiply these two matrices, you get the identity. So, so our least square solution X is going to be this inverse times A transpose times the vector 1, 5, 3. Okay. This, when you multiply these together, I believe you get 1, negative 1, 1, negative 1/2, 1, negative 1/2. Multiply this by 1, 5, 3. And then this becomes 1 minus 5 plus 3, negative 1/2 plus 5 minus 3/2, which is going to be negative 1 and 3. Okay. All right. So that's what X bar is. Now, so that means, that indicates that would be the best, quote-unquote, best solution that we have. And in fact, if we go back to our original system here, if we took X's negative 1 and 3, negative 1 plus 3 is 2. Negative 1 plus 2 times 3 is equal to 5. And negative 1 plus 3 is 2. This of course is, yeah, exactly equal to 5. This is quote approximately equal to 1 or approximately equal to 3. Obviously it's not. These are terrible approximations in terms of, decimal places, but the thing is, this is the quote unquote best approximation that we could get if we wanted to stay in the column space of A. Okay. And in fact, if we going back to the we have our corresponding regression line here, where we have where x. See, in this case, B is playing the role of x and A is playing the role of y. So, in fact, so BA is negative 1, 3. Okay, was from our example, and this tells us that AX plus B is in fact negative 3x plus 1. And so y, if we look at negative 3x plus 1, okay, well that's, did I do that? It was wrong. Of course, this is positive 3 minus 1. Okay. And that starts down here. You'll see that, well, if we plotted our points originally, our original points were 1, 1, 1, 3, and 2, 5. You'll see that 2, 5 is actually on this line. It goes through this point and this point. This point, 2, 5, is on the line, and you can see it just barely misses the 2 other points. Okay, and this is, which means this kind of shows this is actually a pretty good approximation of these 3 points, and we know now that it's the best approximation. Okay, so that's how we get this regression line. So this is what we call the regression line for these 3 data points. Okay, all right, and we're going to talk more about this in the next video. So hopefully there was a lot of theory here. But I'll let you go back and look at this, and we'll continue with part 2 in the next video. Thank you.